Hi, I'm Zor. Welcome to Unizor Education. Today I was going to talk about certain characteristics of ellipses important for planetary movement. But before that, let me just mention a couple of words about Unizor.com website. First of all, it's a totally free website. There are no advertisements, just pure knowledge. It started with the course called Math for Teens, primarily directed towards high school students, certain level of mathematics which not everybody is familiar with, maybe a little bit higher than traditionally taught in schools, with many problems to solve, which I believe is very important. Problems to solve and theorems to prove is something which really develops your mind, rather than just pure memorization of the facts, which students usually forget after passing some tests or exams anyway. So the whole website was dedicated to development of creative thinking, analytical thinking, logic, etc. Then it grew into Physics for Teens. It's another course. Then I wanted to expand mathematics more towards problem solving, so I had a course called Math for All, as well as Physics for All, Relativity for All. There are many different courses on this website, and again, all are totally free. Primarily it's related to these people who can just discipline ourselves and study from the lectures and the written material which is supplemented every lecture. So basically, if you go to a specific website on the unizor.com on a specific page, you will see the video presentation of some lecture, and on the same screen you will see the notes, which basically are like textbooks, and you can just do both basically to make sure that you understand the material. So I do recommend you to go to the website unizor.com, even if you found this particular lecture on YouTube or somewhere else, because it's a course. On the unizor.com you have a whole course, because certain lectures are interrelated. I'm usually using something which I have, let's say, proven or explained in one lecture. I'm using it in subsequent lectures, so it's very important to actually go sequentially, one lecture after another, to cover the course. Okay, now back to today's theme, more about ellipses. Excuse me. So basically, whatever I was talking recently and I'm talking today right now, it's all about movements in central force field. More precisely, you can talk about planetary movements around the sun. The sun being basically a central force, and the gravitation field, which is basically around the sun, can be considered as a central gravitational force. Now, since our planets are moving around sun on ellipses, and we will talk about this in future lectures, it's important to have a little bit more characteristics of ellipses over and beyond whatever has already been explained. I did cover ellipses in mathematics course, Math for All, in geometry, and there are certain properties which I'm explaining right now as part of the physics course, because again it's important for planetary movements. Well, research, studying, whatever. Okay, so today we will talk about three different things about ellipses. Now, in all cases, what's important about ellipses is, in this particular case at least, in this particular way of using ellipses, is to consider them not in traditional Cartesian system of coordinates, but also in a polar system of coordinates. Why? Well, the reason is kind of simple, because if you will start analyzing how the planets or any other actually bodies are moving in a central gravitational field, if you will use just Cartesian system of coordinates, you will have pretty complicated differential equations. And using certain, maybe tricks, I should say, and polar system of coordinates, you can actually reach the result. Like, for instance, you can reach the proof that our planets are moving in ellipsoidal in ellipses around the sun. It's easier to prove it this way. So that's basically the most important justification, and that's why in today's lecture I will spend a certain amount of time basically explaining certain features of ellipse from the polar standpoint, from the polar system of coordinates standpoint. And when we are talking about polar system of coordinates, we usually talk about the following. So if you have an ellipse, it has two axes and two focal points. So this is called the major axis, and in Cartesian coordinates of this is minus a and a. So a is basically the half of major axis. Now b and minus b, b being a minor axis. Now this point is minus c and this is c. So c is half of the focal distance. And in all the cases which I will be talking about, as far as polar coordinates are concerned, my center would be in one of the foci, and the baseline would be basically the major axis. So this is a position vector from one of the foci, which I have chosen as origin of polar coordinates, to position at time t of the body. So this would be an angle theta, and theta obviously is also dependent on time when object is moving around this trajectory, and the distance, well, this is vector, but the distance r from focus to a point is just r without the arrow on the top, and this would be the description of trajectory, r as function of angle theta. And as far as we are talking about ellipse, in this particular way to present the ellipse with this as a origin of polar coordinates and major axis being the base axis, in this particular case the ellipse can have an equation of this. Where a is major axis, e is eccentricity, c divided by a, and by the way, b square plus c square is equal to a square, because the distance between this top and any of the foci is a. This is b, this is c, so this is a Pythagorean theorem. Now, all of this was actually explained and proven in the corresponding lecture in geometry when I was talking about ellipses. Now, this is part of the course called Math for All, and in the geometry part of this, there are basically a few lectures dedicated to ellipses, parabolas, and hyperbolas, all the curves of the second order as we are talking. So all this was covered before, and I'm using it as is. Okay, now my first problem is Using the polar representation of the ellipse, representation in polar coordinates, my first problem is to express the two axes, major axis and minor axis, A and B, in terms of this function. So that's my first problem. Okay, how can we solve it? Well, let's just think about it. If theta is equal to 0, my point is here, right? So what's the distance? Well, that's A plus C. So basically A plus C is equal to R of 0. Well, let's just think about it. If you will try to actually derive this from the formula of ellipse, you will see exactly the same thing. If you will put theta equal to 0, cosine is equal to 1, so you will have A times 1 minus E squared divided by A 1 minus E. So it will be A times 1 plus E, correct? 1 minus E squared divided by 1 minus E is 1 plus E, which is equal to A plus A times C divided by A, which is C. Okay? That's exactly what we were talking about. If theta is equal to 0. Okay, if theta is equal to pi, so we are going all the way 180 degrees, and my point P of t is here. What is this distance? Well, this is A minus C, right? So if A minus C should be equal to R of pi, correct? Well, let's try to calculate it. Again, this is equal to minus 1, right? If theta is equal to minus pi, then the cosine of minus pi is minus 1. So it's 1 plus E. 1 minus E squared divided by 1 plus E is 1 minus E, which is what? A times, A minus A times C divided by A, so it's A minus C. Exactly as we were predicting. Alright? So it's all either intuitively following from the picture or from the formula for ellipse. From this, we can very easily find A and C in terms of R. If we will add them together, C and minus C will cancel and we will have 2A. So A is equal to 1/2 of R of 0 plus R of pi. Now, if we will subtract one from another, A will cancel out and we will have 2C. So C is equal to 1/2 of R0 minus R of pi. Okay? And B can be calculated from here. So B square is equal to A square minus C square. A square is 1/4 R of 0 square plus 2R of 0 R of pi plus R pi square. Now C square will have exactly the same thing, except it will be minus 2. So what will remain, because R of 0 square and R of pi square will cancel out, if I will subtract square of this minus square of this, and I will have only 2 R of 0 R of pi from this, minus minus, so it's plus, again 2, the same thing, R of 0 R of pi. So it will be 4 divided by 4, so it will be R of 0 times R of pi. So B is equal to square root of this. So this is basically the end. We have expressed both half of the major axis, which is A, half of the minor axis, which is B, which is square root of this, and also half of the focal distance C, which is this. So everything, all geometrical elements are following from basically the function which express in polar coordinates the ellipse. That was my first problem, and that's how we solved it. Okay. Next problem. Next problem is area. Okay. Let's talk about area of ellipse. So again, let me start from intuitive kind of understanding of what is the area of ellipse, and then we will basically, very briefly, I will talk about more rigorous definition of this. Okay, let's just compare two things. Let's say this is a circle of radius a, and this is the ellipse of major axis the same, a minus a, but minor b, minor axis to b. And let's compare the area of these two things. Well, if you remember from previous discussions about area in general, in general, area is usually explained as something like an approximation. In this particular case, let's just have one bar, vertical bar. Now, you can calculate the area of this vertical bar by multiplying this width by this height. Now, if you have height expressed as a function, so let's just forget about the bottom half and consider only the top half. Now, remember what is the equation of the circle? It's this one, right? So, if we will concentrate only on top half, I can resolve it. Y is equal to square root of a square minus x square, or yeah, that's it. That's enough. Now, what about the ellipse? Again, in the previous discussion about ellipses in the course of geometry, we were talking about expression ellipse in Cartesian coordinates like this, where a and b are half axis, major and minor. From this, y square is equal to 1 minus b square divided by a square x square, right? Or b square divided by a square minus x square. Am I right? A square. A square that right? I multiply by, no, wait. I multiply by b square, so it's b square, right? Multiply by b square, so it will be b square minus b square divided by x square. And now I'm just doing this. Okay, from which y is equal to b over a square root of a square minus x square. So y is the ordinate, right? So what do we see? Compare this for circle and this for ellipse. Well, this y is greater than this y. This is the ratio, actually. So this one, b is smaller, so the ellipse is smaller. The height of this bar for ellipse is smaller than the height of this bar for circle by this factor. Now, if I will divide the area into infinite number of infinitesimally narrow bars like this, every bar which belongs to a circle will be greater than the bar which belongs to the bottom part of this, belongs to an ellipse. And the ratio will be always like this. So the ellipse bar will be by this less than the circle. So if I will add them up together, doesn't really matter that it's an infinite number of bars of infinitesimally small widths. It's still, the ratio will be exactly the same, no matter how small the division I will do. Which means that the area of a circle is greater than the area of the ellipse, and the ratio will be exactly the same. So, the area of the circle is pi a square, right? A is a radius, basically. Which means that the area of ellipse should be pi a square times this ratio, b over a, which is pi a b. And indeed, if a is equal to b, if a is equal to b, so if ellipse is actually a circle, then we will have the same pi square in this particular case, right? Okay, so this is the area of an ellipse. That's all. That was my second problem, which we have solved. Again, all these will be important when I will talk about planetary movement, about Kepler's law, etc. So it's all preliminary. Okay, and the third problem which I would like to talk about is more of a physical kind of thing. What if my ellipse is not just an ellipse, but a trajectory of the movement of some object? So we have some object and it moves along this elliptical trajectory. I would like to talk about the periodicity, about movement which is periodic, and that's what planets actually are doing. They are periodically moving around the sun. And in this case, what does the periodicity actually mean mathematically? Mathematically, it means the following. Angle theta, we are talking about movement, so angle theta is actually a function of time. Now, as angle is moving, then obviously function r, which is function of theta, the length of this position vector, is actually a function of time. Okay. Excuse me. Okay. Now, how to mathematically express this periodicity? Very simply. If I will increase my time by a period, t, my angle should actually return to the same to the same value, but plus 2 pi, right? So it will be of t plus 2 pi. That's what periodicity means. If my time is increasing by the period, which is the full circle, my angle should actually be incremented by 2 pi, by 360 degrees. So that's basically the law of periodicity for movement along this trajectory in polar coordinates, where theta is actually an angle from the base of the polar system, base axis, towards the position vector. Okay. Now, I would like to connect the periodicity, the t, with an area, which is basically area of the ellipse. And for this reason, I will introduce a function a of t, or a of angle theta, doesn't really matter. This is the area of this sector of the... So if by the time t, my angle increased from 0 to theta of t, now the function a of t is the area which this position vector is swiping during this particular time. It's a function of time, or function of theta, which is function of time. So for any theta we can actually talk about this area, or for any time, if we know how theta is actually changing with the time, then for any time we can have the theta, and again we have some kind of a piece of the sector, if you wish, of the ellipse. Okay, if we know this function, what can I take? What can I tell in this particular case? I can tell the following. If I will substitute the whole period capital T into this function, it means my angle would actually go from 0 all the way to 2 pi, which means this area should be equal to the area of entire ellipse. That's what it means. And if I know something about this function, I can actually, for example, I know how it's actually expressed as a function of t. For example, if a of t is equal to k times t, so it's proportional to time, just for example, then knowing this, I can say that kt is equal to pi ib, and t is equal to pi ab divided by k, if I know that k is some kind of a constant, okay? And by the way, this will be the case, because this is one of the laws of Kepler, which we will prove. However, again, my point right now is that if I know the way how this function looks, then I can actually determine actually the period of rotation along the elliptical orbit based on geometrical characteristics of the trajectory itself. So trajectory, geometry of trajectory defines the periodicity. But again, obviously, only if I know how my area as a function of time actually is looking like, and I will. So basically these are three different things which I wanted to pay attention to. How to express axes as functions of polar representation of the ellipse. What is the area of the ellipse based on these minor and major axes, and how periodicity is related to the area of the ellipse. Okay, I do suggest you to read notes for this particular lecture. So you go to unizor.com, go to Physics Plus for all, and this is part which is called Laws of Newton, and in there I have a lot about different things about, for instance, curves of the second order, and also this particular lecture is more on ellipses. Okay, that's it. Thank you very much, and good luck.